All right, in today's lesson, we're going to be talking about equivalent trig expressions. We're going to go through a warm-up here, and this may be a bit of a trickier lesson. This is definitely going to be a longer lesson, so I'm going to try and take it as slow as possible. I really encourage you to pause the video and try to digest sort of the information that I'm saying, as that's going to be the way that you have the most success in understanding this. Okay, essentially the idea behind equivalent trig expressions is that you're able to express one trig ratio as a different one. So if a question says sine, you can actually evaluate it using cosine. And let's take a look at what this looks like on a graph very quickly and why we can do this. So I've graphed a sinusoidal function here, and there's a lot of different ways that we can actually write this function. The first way that I see goes, and I'm going to just make that thicker, is this graph here. And that's obviously going to continue going down. That's our sine graph. It's just flipped vertically. So that would be negative sine of x. Another way that you might see it would be as a negative cosine, starting with the negative there. So a negative cosine, and then there's also been a horizontal shift for it to start at pi over 2, so it would be x minus pi over 2. A third, let's see how many we can do here. I could do a sine graph that starts at negative pi, right? So that's a normal sine graph. It's just been shifted pi to the right. I could do a positive cosine graph here. It's just been shifted pi by 2 to the left. And then one more. Where else could we go with this? We could do a sine graph that starts at pi instead, so shifted that way if you wanted. Anyways, there's lots of different ways that we can write this exact same graph, and you're going to get the exact same thing, right? And that's the idea behind it, is that there's different ways of writing different things. And instead of talking about graphs, we're going to be talking about ratios, as we have for the last couple of videos here. So let's start with our first pattern. The first pattern here, I've just given it a title of a Q1 pattern. I don't know if this is actually what it's called, but that's what I'm calling it. So we're going to take a look at our special triangles here. We're going to be using degrees for this because I feel people are more comfortable with degrees, and then at the very end, when we conclude our investigation, we'll put it back into radians. So we're going to look at our first special triangle here, our 30, 60, 90 triangle, and we can fill in the blanks here for all of our sides. 30 is the smallest degree, it's across from the smallest number, 2 is the hypotenuse, and then root 3 is what's left. And I'm just going to fill in these ratios here. So sine of my 60, so this is going to be 60, and I'll do these 3. Sine will be root 3 over 1, and yeah, I know I could simplify it. No, not root 3 over 1, root 3 over 2. Cosine of 60 will be 1 over 2, and then tangent will be root 3 over 1. And I know I could simplify that. I'm just going to leave it right now. Let's do our 30 degrees. So sine of 30 degrees will be 1 over 2. Cosine of 30 degrees will be root 3 over 2. And tan of 30 degrees will be 1 over root 3. So we're starting to see some repetition here in the results, and that's what I was hoping that you would notice. Notice how sine of 60 and cosine of 30 give you the same result. Interesting. Notice how sine of 30 and cosine of 60 also give you the same result. Now, tan of 60, tan of 30, obviously those don't match, but what if I did cotangent of 30? That would flip, right? It would be, once again, root 3 over 1. Aha! And here we have a partner for tan of 60. Tan of 60 matches with cotangent of 30. We get the exact same angle. Interesting, interesting. Let's keep this top of mind. We're going to come back to this idea in just a sec. Now remember that all angles in a triangle add up to 80 degrees. Okay, this is going back to elementary school here. How can we express one unknown angle with respect to the other? So if we know that this angle, let's say, is 25. I'm just picking a random number here. We know that this one's 90. We're being given a square here. And so if I needed to figure this guy out, well, I would say the interior angles are 180. I would subtract 90, and then I would subtract 25. All right, that's not bad. I could simplify that, and I could just say, well, what's 90 minus 25? I don't know why I'm not writing the 0 in 90. 90 minus 25, it would get you that guy. In our special triangle, this angle is 30 degrees. And if you forgot what the other angle was, how would you get there? Well, you'd go, what's 90 minus 30, right? We can agree that 60 is 90 minus 30. Just like 30 is 90 minus 60. So what we're going to do now is we're going to rewrite our second set of ratios from above, so from the first page, so that instead of 30, I'm going to write 90 minus 60. So I'm going to write sine, and instead of 30, I'm writing 90 minus 60. Cosine of 90 minus 60, and tan of 90 minus 60. I'm just going to zoom out here so I can see them. What was sine of 30? It was 1 over 2. What was cosine of 30? It was root 3 over 2. And what was tan of 30? It was, or we'll do cotan. Cotan of 30 was root 3. But then we also noticed that pattern, right? We said, well, sine of 30 matches up with cosine of 60. We got 1 over 2. So down here, I'm just going to keep writing. I'm going to say, well, that's the same thing as cosine of 60. Cosine of 30, root 3 over 2, matched with sine of 60. So we'll write sine of 60. Then cotangent of 30 matched up with tan of 30. Nope. Tan of 60. Not tan of 30. Tan of 60. There we go. Why is this interesting? Because look at the number here. The second number in our bracket matches up with the exact angle which is being applied to those ratios. I wonder if this proves true, this sort of pattern here, for any angle. Let's give it a test. Let's say instead of doing 30 or 60, let's do 37. I'm going to say sine of 90 minus 37. Let's see if that's going to be equal to cosine of 37. So I'm going to take my calculator. Sine of 90 minus 37. Well, 90 minus 37 is 53. And I'm going to make sure I'm on degree mode here. Sine of 53 is 0.799-ish. Cosine of 37. Let's try that. Cosine of 37 is the same, 0.799. Interesting, interesting. Let's do it again. Let's try a different one. Let's do a cosine first. Let's do cosine of 90 minus 51. We think that that's going to be the same thing as sine of 51. Okay, okay. Well, what's 90 minus 51? 39. Let's do cosine of 39. That's 0.777. Lucky me. Sine of 51. Let's try. Oh my gosh. It's the same. So it totally works. Okay. We have these relationships up here, and so we can summarize the patterns like this. Okay, what is the pattern? We'll do it in degrees and then we'll put it in radians first. Sine, cosine, and then remember we had to be weird on the last one. We had to say cotangent. And if you go 90 minus any angle, that's your theta symbol. If you're unfamiliar with it, theta is like a funny zero, just with a line through it, and theta is often the variable that we use for unknown angles. If we had sine of 90 minus an angle, we could simply evaluate it using cosine of that angle. Cosine switched to sine of that angle, and cotangent switched to tangent of that angle. That's pretty cool, eh? Sort of useful in math homework questions, right? But neat that there's that pattern there. If we wanted to write this in radians, the pattern exists. It's the exact same because radians are just a different way of writing angles. Except instead of 90 degrees, we write pi over 2. Take away theta. Take away theta. Take away theta is equal to cosine of theta, sine of theta, tan of theta. Okay, it exists all the same. Pretty interesting pattern for angles in Q1. Okay, let's continue now and let's look at a pattern for angles in Q2. Okay, we're going to continue with our 30, 60, 90 triangle. I'm just going to redraw it on here, the one that we were just dealing with. Let's do better. That's probably closer. So we had 30, 60, this was 90. My hypotenuse was 2, my short side was 1, across from 60 is root 3. Okay. In this triangle, this is my terminal arm because it's the one starting from the origin. Very first thing I want us to do, and let's just typo here, let's rotate the terminal arm by 90 degrees. So I rotate the terminal arm, and I'll do this in a different color, by 90 degrees. And it's going to look something like that, probably. Drop it down. Okay, if I rotate it by 90 degrees, my interior angle here is the 30. This sort of top angle here is the 60, and then I have a right angle. My hypotenuse is still 2. No, sorry, I shouldn't be drawing my triangle against the y-axis. I should be drawing it against the x-axis. My apologies. Okay, I draw my triangle down. There, that looks better. I knew something looked off. Okay, I rotated. It's been rotated. Now what makes more sense, here we go, is that this top one is 30 degrees. My bottom one here is 60 degrees. And I have my right angle right there. Hypotenuse remains at 2. The side across from 30 is 1, and the last side is my root 3. And I'm just going to make sure that I match with my cast rule, right? That I have things that are positive, they're supposed to be positive. Things that are negative are supposed to be negative. Hypotenuse is always positive. My root 3 here is in the positive y-axis, so I'm good. However, my 1 is now on the negative x-axis, so I have a negative symbol out front there. Okay. What I'm going to do now is I'm going to rewrite our primary trig ratios for the updated triangle, okay? And how far has my triangle been updated? How much has it, what angle is this, right? This was a 90, and then I rotated it, and this interior angle here is 30. So the angle that I'm dealing with here is 120 degrees. So I'm going to rewrite it now using my cast rule, using my triangle for 120 degrees. I have sine of 120, cosine of 120, and then tan of 120. Okay, well, what's sine of 120? 120 lands here. Sine of 120 is going to be root 3 over 2. Cosine of 120 is going to be negative 1 over 2, right? My adjacent over my hypotenuse. And last but not least, my tan of 120 is going to be negative 3, root 3. My opposite over my adjacent. Okay, cool. And now we're going to write them a third time, except we're going to demonstrate the fact that we actually rotated this 90 degrees by writing 90 plus 30. Okay, so sine of 90 plus 30 is root 3 over 2. Cosine of 120, no, it's not 120, it's 90 plus 30. Is root 3 over 2, and then tan of 90 plus 30 is negative root 3. If we were to go back to our original investigation that we did on the very first page, I've seen these numbers before, and in fact it's sine, oh, I wrote one of these wrong. Cosine is not root 3 over 2. It is negative 1 over 2. That's better. Okay, let's go back. Let's look for which guy has a root 3 over 2. Cosine does. Surprising. So in fact, it's going to match up again. Cosine of 30 gives us root 3 over 2. Sine of 30, and in fact it'll have to be negative in order to pull out the negative here, but that gives us negative 1 over 2. And then last but not least, what this is going to end up matching up with is negative cotangent of 30. And again, this is interesting because look, we've got a 30, 30, 30, and that is exactly what it matches up with right there. Okay, so let's test it out now. If I were to be given an angle for something else instead of 30 degrees, does the pattern prove true? We're just going to do one test to confirm that this is right. So let's do sine of 90 plus, 17. And in theory, that should match up with cosine of 17. Okay, well, 90 plus 17 is 107. And sine of 107 is about 0.956. Cosine of 17 is the same. Amazing! And so we can simplify these rules, these Q2 rules once again, okay? These are like more addition, whereas the first ones were subtraction. And we'll write it again for both degrees and radians. So sine of 90 plus any angle will match up with cosine of that angle. Cosine of 90 plus any angle matches up with sine of that angle, negative sine of that angle. And tangent of 90 plus any angle matches up with negative cotangent of that angle. And how does this look in radians? We just write pi over 2 instead. Amazing. Okay, so now let's use some of these patterns to actually do some solving. What these are sort of called are equivalent expressions or co-function identities that you can use to sort of make solving simpler. So our first question here is asking us to write an expression that's equivalent to 5 pi over 12. We're working with radians. I know that in all of my formulas, I either need it to be a pi over 2 plus something or a pi over 2 minus something. What is pi over 2? Let's make that a nice common denominator with our 12 here so that we can see, is 5 pi by 12 just a little bit above or is it a little bit below? Pi over 2 is 6 pi over 12. Okay, so we can see that 5 pi by 12, which is my question here, is just below 6 pi by 12. And how do we get 5 pi by 12? Well, you would take 6 pi by 12 and subtract pi by 12. Or, we already said 6 pi by 12 is the same thing as pi over 2. So 5 pi by 12 is pi by 2 minus pi by 12. Okay, how is this useful? Well, the question is asking us to find an equivalent expression for cosine of 5 pi by 12. And we said that 5 pi by 12 is the same thing as pi over 2 take away pi over 12. Well, that's like our Q1 pattern, right? We had cosine of pi by 12 take away a number, and what did that match with? It matched with sine of that number, that angle, which was pi by 12. Awesome. Let's do the same thing here for sine of 2 pi by 3. Okay, so once again, we need to sort of ask ourselves, what is pi by 3? Is it, or 2 pi by 3, is it pi by 2 plus something, or is it pi by 2 minus something? Well, what is pi by 2? It is 3 pi over 6. We could say that if you want. And then 2 pi over 3 is 4 pi over 6. Aha! So 2 pi over 3 is the same thing as 3 pi over 6 plus pi over 6, right? Because we said 2 pi over 3 is 4 pi over 6, and how do we get that? We have a 3 pi over 6 plus a pi over 6, and a 3 pi over 6 is just saying pi over 2. So we've got a plus sign here. We've got our pi over 2 plus something. That's our Q2. All of our Q2s have a plus sign. And my original question was sine of 2 pi over 3. Sine of 2 pi over 3, we said is the same thing as saying pi over 2 plus pi over 6. And what does sine match up with up here? It matches up with cosine of sort of that angle. That matches with that. In our first question, those two match up together. Awesome. Here's another type of problem that you might see. Given that sine pi by 5 is equal to some decimal place, we need to determine, in this case, cos of 3 pi over 10. So at some point in time in our answer, we're going to be hit with a sine pi over 5. Let's see if we can somehow get there. Can we write cosine as 3 pi by 10? Let's use our Q1 pattern here of pi over 2 take away 3 pi over 10. Okay, I know that 3 pi over 10 is in Q1, which is why I know that I'm using a Q1 pattern, right? 3 pi by 10, if I think of my Q1 here, up here is pi over 2, and 3 pi over 10 is definitely less than that, so it's up in here. Okay, sine of pi by 2 minus 3 pi by 10, can we simplify that? Pi over 2 is 5 pi over 10, take away 3 pi over 10. And oh, look at that. 5 pi by 10 take away 3 pi by 10 is 2 pi by 10. And what is 2 pi by 10 if not pi over 5? And we were given that in the question. Sine of pi over 5. We already know the answer. We don't even have to use our calculator. It's 0.5878. Amazing. Okay, question B is asking us to do the exact same thing. We need to incorporate sine of pi by 5, and our question here is cosine of 7 pi by 10. First, let's take a quick look and see which quadrant it's in. 7 pi by 10 is going to be in quadrant number 2. It is bigger than pi by 2, and remember pi by 2 is like 5 pi over 10. 7 pi over 10 is bigger than 5 pi over 10. So we are working in quadrant 2. And in fact, it would look like this somewhere, with this being pi over 2. Because we're in quadrant 2, we're using one of those formulas with a plus in it. And just thinking out loud here, what if we tried a different strategy? What if we went backwards? What if we said that this was on the tail end? This was the second half of the formula. And we actually had something here because we could express cosine of 7 pi by 10 as an addition of something. Is 7 pi by 10 an addition of something using pi by 2? Well, yeah. Pi by 2 is the same thing as 5 pi by 10. So cosine of 7 pi by 10 is like saying 5 pi by 10 plus 2 pi by 10. Huh. And cosine of 5 pi by 10, 5 pi by 10 is pi over 2. And we can also simplify 2 pi by 10 as being pi over 5. Aha, here we go. What is this addition formula here? What is, if we've got cosine in the brackets with an addition, what does it match up with? It matches up with a negative sign of the second number in the bracket there. And in fact, 2 pi by 10, that number in the bracket, is pi over 5. And that is what we were given at the beginning, right? We were told that sine of pi by 5 is 0.5878. And so we can simplify this. We can say, well, cosine of 7 pi by 10 is negative sine pi by 5, which is negative 0.5878. I'm not going to say there's one right way of tackling these types of problems. These are what the textbook questions are going to look like, so I just thought I'd prepare you for those. You just got to sort of wiggle things around using the formulas and ask yourself, is it a Q1, is it a Q2, and then how can I break it down accordingly? And that's it.